I am mathematics, and for millennia, I have watched you humans try to make sense of your world. And for a very, very long time, your story of how things moved, well, it was elegant, it was intuitive, and it was profoundly wrong. For nearly 2,000 years, your most trusted authority on this whole subject was a philosopher named Aristotle. And his ideas, you see, they weren't based on my complex equations. They just felt like common sense. He built this entire system based on what you could see and feel. A rock falls because, well, its natural place is the earth. Smoke rises because its nature is to be up in the sky. He explained the why of motion. And that story was so satisfying that for centuries, almost no one even thought to question it.
But that story had plot holes, big ones, contradictions that your engineers and your soldiers, the people actually doing things in the real world, just couldn't ignore anymore. I mean, think about it. If you tie a heavy rock to a light rock, does the heavy one pull the light one down faster, or does the light one act like a little parachute and slow the heavy one down? And the military guys knew for a fact that cannonballs didn't fly straight out and then just drop. No way. They followed this beautiful, graceful curve. The cracks in that old story were definitely starting to show.
Then, a man came along who did something truly radical. He stopped asking why things moved and started asking how. And to answer that question, he turned to me. He began to speak my language, the language of numbers. His name was Galileo Galilei. And this was the game-changing idea. That nature wasn't just some story to be told with words and logic. No, it was a code. It was a set of rules that could be deciphered, figured out with numbers and equations. But to read that code, Galileo had a huge practical problem. Falling objects just move way too fast. You drop something and poof, it's on the ground. How could you possibly measure that with the tools they had back then? You couldn't. So he had to get clever. He came up with this brilliant way to slow motion down without changing its fundamental nature. He built this long, incredibly smooth ramp, rolled a polished ball down it, and basically diluted gravity, stretching out time so he could get a good look. He used his own pulse with a stopwatch. Thump, thump, thump. For the first time, a human was systematically measuring motion using my principles. He wasn't just observing anymore. And what he found was absolutely astonishing. So, after one beat of his pulse, the ball rolled a certain distance. Okay, simple enough. Let's call that 1 unit. But after 2 pulse beats, the ball hadn't traveled 2 units, like you might expect. It had traveled 4 units. Not double the distance, 4 times the distance. This was not some simple linear thing. And the pattern just kept going. After 3 beats, it traveled 9 units. After 4 beats, 16. It was undeniable. He had uncovered a fundamental law of nature, hiding in plain sight this whole time. And there it is. For the very first time, the chaos of motion was captured in a precise, predictable equation. The ball wasn't moving at a constant speed. Its speed was constantly increasing. It was accelerating. And maybe the most important part, the weight of the ball didn't matter one bit. But, and this is a big but, this incredible discovery created a whole new, much deeper problem. In describing motion so perfectly, Galileo had accidentally pushed my own language, mathematics itself, right to its breaking point. Think about it. Speed is just distance divided by time. But what exactly is an instant? Well, by definition, in a single instant, 0 time passes. And if 0 time passes, you cover 0 distance. So you're left trying to divide 0 by 0, an operation that, in my language, is just nonsense. It's undefined. It breaks the rules. So how can something have a speed if time itself isn't even moving? Now, you could try to get around it. You could calculate the average speed over a really tiny interval, like 1/10 of a second, then 1/millionth. But no matter how small you make that slice of time, it's still just an average. You get closer and closer and closer to the true speed, but you can never actually land on the exact answer for that precise instant. Galileo had hit a conceptual wall. And look, this wasn't just some abstract puzzle for philosophers. All across your world, very practical people were running into this exact same paradox. They were screaming for a solution. What's so amazing is that all these totally different fields were facing the same 2 fundamental challenges. 1, how do you calculate a rate of change at a single instant, like a planet's speed? And 2, how do you sum up an infinite number of tiny little pieces, like all the points along a cannonball's path? And my tools at the time, the geometry of the Greeks, the brand new algebra, they just weren't built for this. The world that Galileo had revealed, this world of constant, continuous change, it demanded a new branch of math to describe it. A mathematics of motion and infinity had to be invented. Now, before this new math could be born, the old ideas had to be overthrown decisively. And while his true breakthrough came from all that slow, tedious work with ramps, the story that gets told is, well, a lot more dramatic. But this legend, whether it happened exactly this way or not, it captures the real truth of the revolution he started. It captures the sheer earth-shattering drama of the moment. An idea that had stood for 2,000 years was about to be smashed by a simple, observable fact. The story goes, he stood at the top of the Leaning Tower of Pisa, holding 2 iron balls, one 10 times heavier than the other. Now, according to 2,000 years of Aristotelian physics, the heavy balls should have hit the ground way before the lighter one. He released them, and they fell, side by side, perfectly synchronized. It was a testament not to their purpose or natural place, but to a universal law that I had written into the very fabric of your reality all along. And in that single, unified thud as they struck the ground, the authoritative voice of Aristotle was finally silenced, and the age of mathematical physics truly began. So Galileo gave you a new universe, but he also left behind this huge mathematical challenge. A world of continuous change had been revealed, but my tools for describing it were incomplete. The stage was set. The question was, who would be the one to finally provide the answer?